Let's take a look at some problems that make use of the sine and cosine addition and sum formulas that we know. All right, so here's the identity that you might want to prove. The sine of t is equal to the cosine of t minus pi over 2. So supposedly these two things are equal. Now, sine of t by itself on the left, there's not much we can do with that. But on the right, this looks like, it's of the form, I should say, the cosine of a minus b, right? Which we have a rule for that we proved yesterday. That's equal to cosine a, cosine b, minus sine a, sine b. Cosine, cosine, sine, sine. So if we just look at our problem, we can see that t is replacing a, and pi over 2 is replacing b. So I'm going to sub those values in. So we get the cosine of t cosine pi over 2 minus the sine of t, the sine of pi over 2. Alrighty. So let's keep looking at that. Well, the cosine of t is just that. The cosine of pi over 2, the cosine of 90 degrees, right, would be 1. So this is equal to, I'm sorry, cosine of pi over 2, 90 degrees would be 0. So 0 times cosine of pi over cosine t is 0. So that's 0 there. Oh, and then I made a small error here. We have to remember that cosine, if it's minus in here, then it's plus in this side of the formula. It's going to be much better for us. Then we have the sine of t times the sine of 90 degrees, the sine of pi over 2 radians. Well, that's just 1. So this whole thing becomes the sine of t. But that's what you wanted it to be. You wanted it to equal that thing on the left. And notice what I've done here. A good form, logically, is if you want to show two things are equal, you take one side of the expression, and you keep moving it and changing it and using true identities until it looks like the left side of the equation, or the other side of the equation. Okay, here's another identity that we can show. So watch this. The cosine of t equals the sine of t plus pi over 2. Okay, well, let's look at this side. This looks like the sine of a plus b, so I'm going to write this as the sine of t cosine pi over 2. I'm thinking sine, cosine, cosine, sine. Plus in the middle there. Whenever it's the sine of a sum of angles, then you'd see that it would be plus here. But if it minus, it would be minus. The sign generally agrees here. Sine pi over 2. So there you go. If we take a minute to figure these things out, cosine pi over 2 is again 0, so this first term is gone. Plus over here you've got the sine of pi over 2, but that's just cosine t times 1. So this whole thing equals the cosine of t, and that's exactly what you wanted. So let's look at another one that makes use of some sum and difference formulas. So here's an expression. The sine of the ln of xy. Okay? And suppose you're given the following facts. The sine of the ln of x is equal to 1/3. The sine of the ln of y is equal to 1/5. And then you also know that 0 is less than the ln of x is less than pi over 2. And 0 is less than the ln of y is less than pi over 2. Okay, so here would be some advice. First off, this is sort of a strange thing to see, but I'm taking the sine of the ln of something. So that might bother you a little bit. But all that's really saying is that this ln of x expression is really like acting like an angle. So I'm taking the sine of an angle called ln of x. And I'm also taking the sine of an angle called ln of y. And that makes these two statements a lot easier to understand, because what are they saying here? They're saying the angle ln of x is between 0 and pi over 2. And they're saying the angle ln y is between 0 and pi over 2. That's a fancy way of saying that these angles are acute. So we'll be able to draw some right triangles in the first quadrant in a little bit. But first things first, let's see what we're even dealing with. This is the expression we want the value of. And it sure doesn't look like the sine of a plus b or the sine of a minus b or anything like that, unless we use our rules of logs. And we know that we can write this, the sine of the ln of x plus ln of y. That's because of the first rule of logs that we proved a long time ago. Okay? So now that we have that, we now know a rule for the sine of a plus b. It's sine, cosine, cosine, sine. And I can sub in what I know. This is going to be ln of x, ln y plus ln of x, ln y. Put parentheses around that, make that clear that those are the angles. Okay, so you should look and see what you know already to get started. So I know what the sine of the ln of x is. Right there, it's 1/3. So this first expression I can replace with 1/3. The cosine of the ln of y, I was not given that fact, so I'm going to leave that blank. The cosine of the ln of x I was not given, so I'm going to leave that blank. And then the sine of the ln of y is 1/5, and that I do know is 1/5. So there we go, I can plug that in. All right, so I need these two missing values. So let's talk about the first one. Let's talk about the cosine of ln of y. I'd like to find that. Well, the only fact I know about ln y is that the sine of ln of y, this thing, is equal to 1/5. And I know that actually it's two facts. I know it's an acute angle. So I'm going to draw a right triangle in the first quadrant, and I'm going to label this angle in the corner ln y. So what do we know? We know that the sine of the ln of y is 1/5, so that means opposite ln y is 1, and the hypotenuse has to be 5. Okay? What makes this problem a little harder than when we did yesterday is that this is not a pretty 3, 4, 5 right triangle or 5, 12, 13 or something. We don't know this side. We're going to do Pythagorean Theorem. X squared plus 1 squared equals 5 squared. That means x squared equals 24, or x equals the square root of 24. Well, now that I know that adjacent side, I can get the cosine of the ln of y. It's going to be adjacent over hypotenuse, or rad 24 over 5. All right, let's do the other one. So this one could go pretty quickly. Cosine of the ln of x, I could again draw a triangle, a right triangle that is, in the first quadrant, because we're talking about an angle between 0 and pi over 2 radians. I'll put ln x in the corner here. We know that the sine of the ln of x is 1/3, so I'll put that fact here, 1 here, opposite as 1, I'm sorry, hypotenuse is 3. Do Pythagorean Theorem, this is going to turn out to be the rad of 8, so then this is rad 8 over 3. Okay? So now you have that expression. If you want, you could simplify it a little bit, but you really have the answer at this point. It's going to be rad 24 over 15 plus, that came from multiplying the numerators here, and then here you're going to have rad 8 over 15. So while we're at it, why don't we just reduce this? Rad 24 you can divide by rad 4 and rad 6, so it would become rad 4, rad 6 over 15. This one's going to become rad 4, rad 2 over 15. So what can we do now? This is 2 rad 6 over 15 plus 2 rad 2 over 15, right? Now you can't add rad 2 and rad 6, they're not the same. If you want, you could factor out that 2/15, make it 2/15 times the square root of 6 plus the square root of 2. Any of these answers are equivalent and the same, but it's good to practice rewriting things because in the future, you have multiple choice questions. Most of the time, you're going to have to match up your choice to something that's already there. So let's look at another question. I want to remind you something from that you've done before. All right. So in the past, you've learned about things called function composition. So for example, if I said f of x equals x squared, and then I had another function, maybe f of x equals x plus 2. I'm sorry, not f of x. Let's give it a new name. Let's call it g of x. Then, that's a mistake too. I said g of x equals x plus 2. Then I could ask you another question. For example, like what's f of g of x? Or what's g of f of x? When you ask these kinds of questions, they're called function compositions. You're taking one function and you're subbing it into another function. You're having it replace x in the original. So when I look at this, here's the original function, f of x, says whatever x is, we're just going to square it. So when I see f of g of x, what we're saying is g of x is taking the place of where x used to be. And what does f do to something? Well, f just squares whatever you give it, right? So this is going to be g of x squared. Okay? But then g of x is just x plus 2. So this is really x plus 2 squared. So that's called the function composition. Now what's sort of fun is to try and do the composition in the opposite order and see what happens. Okay? So now what we're saying is that in the g function, we're going to replace x with f of x. So g of x takes whatever you give it, and it just adds 2 to that number, or to that expression. Right? So if I said, hey, what's g of d? That's just d plus 2. Just adds 2 to whatever you have. So if I said, what's g of f of x? That's just f of x plus 2. But f of x is really x squared, so you get x squared plus 2. So that's called a function composition. So I'm showing you this because, first off, you should review it. And secondly, you should notice function compositions are not commutative. Okay. So I want to consider this next problem. So let's pretend I asked you to consider this expression. F of x plus h minus f of x over h. Now I'm going to say this. If you haven't seen this yet, you will. And at some point, it's going to be very familiar to you. You're going to be very comfortable with what this thing is. It has a name. It's called a difference quotient. That's what usually it's referred to as. And let's pretend for a minute that f of x is the function sine x. So what we're going to do is we're going to find the difference quotient if f of x equals sine x. Okay, so here we go. F takes the function, whatever it is, and it does the sine of that. Whatever you give to f, it'll take the sine of that expression. So if I look at this piece right here, it's saying take the sine of x plus h. If you're confused about that, think about it this way. Where x used to be, right here, is now x plus h. So it's got to get replaced in this x also. So then this is minus f of x. Well, that's just the function sine x over h. Okay? So what we've done is we've evaluated the difference quotient for the function f of x equals sine x. Okay. Now, it can be shown that this thing here equals sine x times cosine h minus 1 over h plus cosine x times sine h over h. So you can show that that relationship holds, and that's what we're going to do now. All right. So we want to show that this thing in blue is equal to the thing in red. So what we're going to do is we're going to take this thing in blue and we're going to start rewriting it. Well, I know stuff about sine of x plus h. That's equal to the sine of x, the cosine of h, plus the cosine of x, the sine of h. Then I have minus sine x, whole thing over h. Okay. So now, when I look at the expression in red, I notice a few things. First off, I notice over here, I have cosine x times sine h over h. And then if I look at my expression down below, there's the same term. So I'm going to reorder things a little bit on the bottom here. So here's what I'm going to do. I'm going to leave that sine x cosine h first. And then I'm going to take the minus sine x and bring it over next to that. Say minus sine x. And I'm going to put that over h. And I'm going to say plus cosine x sine h over h. So this is just a simple reordering of things. And then additionally, I know that if I have a bunch of things being added or subtracted over one denominator, I can split them up into 2 fractions or 3 fractions or more. Let's keep going. So I look at this expression, and then this thing over here on the right I'm really happy about. That's just the cosine of x times sine h over h. But that's exactly what I wanted it to be. There it is. So I took care of that part. Problem is I don't have this yet. So what I notice is it looks like the sine x could have been distributed into this, which means it also could be factored out. So if I look at this expression on the left, sure enough, if I look in that numerator, notice, look, there's a sine x here and a sine x here. So I'm going to factor that out. That's what I'm going to do. I'm going to put the sine x out in front. And then inside, to get that numerator, I would need cosine h minus 1 over h. So there you go. And that's exactly what I wanted to show. I've taken the thing that was on the left. I've taken the expression that's circled in blue there, and I've turned it into the expression written in red. That's how you... So here's another proof. We want to prove that the sine of u plus the sine of v equals 2 sine of u plus v over 2 cosine of u minus v over 2. So I'm going to do is we're going to take each one of these things separately. First off, take a look at this piece for a minute. And let's write it this way. 2 sine of u over 2 plus v over 2. And the nice reason to write it that way is because now it looks like sine of a plus b. So we can use our identity. Okay? So let's do that. So let's also keep in mind that this is just 2 out in front being multiplied by all of this. So I'm going to put a big bracket here for the time being. I'm going to do the same thing over here. I'm going to write this as the cosine of u over 2 minus v over 2. Okay? So here we go. So 2 bracket, and to get this piece, it's going to be sine u over 2 cosine, cosine, sine. Right? Sine, cosine, cosine, sine. So what do we have here? V over 2, it's plus, because sine always matches. And then you got u over 2 and v over 2. All right, so this looks like it's getting very messy very quickly. And we're hoping that this thing in blue turns into that expression. Right? Let's see what happens. Let's go over here. And then we have that thing, right? Times what? So the cosine of u over 2 cosine v over 2 minus, or I should say plus, because cosine is the opposite, right? And then what do we have here? Sine u over 2 sine v over 2. Okay. All right, so looks like we have to commit to multiplying these things. So we'll multiply that, right? That pair, and this pair. So what do we get? Well, you're going to have, in the first case, you're going to have the sine of u over 2 times, and I'm going to pick a careful order. I'm going to do this one and then this one, cosine u over 2, and then I have cosine squared v over 2. So there's my first term. All right. Let's do the outer pair. So plus. And I have sine u over 2 times this sine u over 2. So that's going to be sine squared u over 2. And then I'm left with the cosine of v over 2 sine of v over 2. Okay, let's make sure this looks like cosine squared and we're not confused. That's cosine squared, not cosine squared, sine squared, u over 2. Okay, let's keep going. Plus the next term. This times this is going to be cosine squared u over 2. And I just got really happy because I'm looking at this thing and I'm thinking, wait, here's a cosine squared u over 2. Here's a sine squared u over 2. That's making me think about the number 1. All right? If we keep going, we end up with the sine of v over 2 times the cosine of v over 2. All right? And now plus, here comes our last term. It's going to be cosine u over 2, sine u over 2, and then sine squared v over 2. So cosine u over 2, sine u over 2, and then sine squared of v over 2. And again, I'm happy because I see this thing, and somewhere over here, here's a cosine v squared over 2. So this is actually looking pretty promising. Don't forget, this whole thing is going to get multiplied by 2 at some point when we get a chance. Okay. Don't forget what we're hoping for. This is going to turn out to be sine u plus sine v, supposedly. So let's see what happens. What would be nice is to try and add some like terms. And we actually can. Let me show you. This term here and this term here have sine u over 2, cosine u over 2 in common. So I'll make this in blue. I'm going to make this sine u over 2, cosine u over 2, factored out of cosine squared v over 2 plus sine squared v over 2. Look at the blue, and that's what I've done. I factored out the common factor. Plus, and here we go. Get ready. If we look at the other two terms, we'll circle those in green. Notice how they have cosine v over 2 sine over VO2 in common. So it's going to be plus, here we go, sine v over 2 cosine v over 2 times cosine squared u over 2 plus sine squared u over 2. Again, this whole thing is going to get doubled at some point. Well, this turns out to be very pretty all of a sudden. Very pretty. So if we look at it, what do we notice? We see that this is equal to 1, and that's equal to 1. So this whole expression turns into 2 times the sine of u over 2 cosine u over 2 plus sine v over 2 cosine v over 2. Okay. So now this does not look like sine u plus sine v. But there's one more clever realization we need to have. This is as tricky as they get, really. All right, so here's a fact we learned in the past. So recall for a minute, you learned this, that the sine of 2 theta is 2 sine theta cosine theta. Right? So what does that mean? What that means is that if we multiply both sides by a half, we'd have a half sine 2 theta equals sine theta cosine theta. Well, now this gets beautiful, because if you look at each of these expressions, they look exactly like this. So here you go. 2 times, and this is really this thing. It's going to be 1/2 the sine of, and if we're careful, right, that is just the sine of u, because it's going to be u over 2 plus u over 2, or u over 2 times 2, really. It's 2 theta. Just like this one is plus 1/2 the sine of v. And after all that long walk through the woods, and we didn't know what we were doing, we distribute the 2, and we get what we hoped we wanted. Wow, now that is a pretty problem.